Okay, so another kinetics video, and this is going to be focused on rate laws. So figuring out the rate law related to both experimental data and a reaction mechanism. So the rate is dependent upon the concentration of reactants. As the concentration of reactants goes down, the rate of the reaction is going to decrease because you have less reactants bumping into each other. And each reaction has a unique rate law. And the way that we write a rate law in general is rate equals some constant k times the concentration of your reactant to some exponent. We call that that exponent the reaction order. And same thing for my other reactant. The reaction order could be 0, it could be 1, it could be 2. And you cannot predict the reaction order just by looking at the overall chemical equation. You have to either have experimental data or know the reaction mechanism, and usually we find the reaction mechanism based on experimental data. So you have to have some data. Just looking at the balanced chemical equation will not tell you what the reaction order is. So possible reaction orders for a reactant, it could be 0 order, 1st order, or 2nd order. You will never see a single reactant having 3rd order or above. And thinking about what that means, 0 order means that in the rate law that the concentration is to the 0 power. So anything to the 0 power is going to be 1. So notice that if you change the concentration of a reactant at 0 order, the rate will not change. It doesn't matter what the value is. 1st order, the concentration will be raised to the 1st power. So for example, if you double the concentration of reactant A, the rate of the reaction will also double. And then if it's 2nd order, if you double the concentration of this reactant in this case, the rate would go up by 2 squared. So it would quadruple. Here's an example of some data that you might get to determine the rate law. And you'll notice in this example, you want to make sure you compare experiments in which only the concentration of one of your reactants changes. So if you notice in experiment 1 and 2, the concentration of NO is double what it is here, but then my concentration of H2 is the same. And so you'll notice if I compare these, going from 2 to 1, I double my concentration of NO, and my rate quadruples. So that tells me that NO is 2nd order. So I take the concentration and I square it. And looking back at H2, you'll find that it is 1st order for H2, because when I look at these two, it looks like my concentration goes up by 1.5 times, and my rate is changed by the same amount. It goes up by 1.5 times. So this would be my rate law for this reaction. It's 2nd order for NO, 1st order for H2. We could say overall it is 3rd order. And you could also find the value of K by going back to your experimental data and just plugging some values into your rate law, and then that will give you a value of K. And make sure you pay attention to units when you do that. So in this case, you've got molarity per second, divided by molarity squared, divided by molarity. So your answer is in 1 over molarity squared seconds. So overall reaction order, you just add up the order of the individual reactants. And these rate laws are related to reaction mechanisms. So most reactions do not occur in just one step. For example, this reaction occurs in 2 steps. One in which 2 NO molecules collide, and it forms something we call an intermediate. And then that intermediate collides with an oxygen molecule, and that is what forms the product. So you can have a multi-step reaction mechanism. So an intermediate is something which is formed in one step and consumed in the next. It's not a reactant or product. Another vocab term is molecularity. So that refers to how many molecules are involved. So unimolecular is 1 molecule, bimolecular is 2 molecule, etc. And what happens in a mechanism, some steps will be faster or slower than others. The slow step is called the rate limiting step. That's the step that determines your rate law. And if we look at this overall reaction, and it has 2 steps here. Here's step 1, here's step 2. We are told that step 1 is the slow step. The way that you find the rate law for the overall reaction is you look at the molecularity of those reactants in the slow step. So in this case, my slow step has 2 molecules of NO2. So my rate law for the overall reaction is rate equals K NO2 squared. Notice how CO does not show up in my rate law at all. And that's because CO is not involved in my slow step, so it doesn't affect my rate. If there's an intermediate involved in the rate limiting step, let's say my slow step is the second step, it involves NOBR2. NOBR2 is not a reactant, it's actually an intermediate. What you would do is you would go back and you would initially you'd want to say that my rate is NOBR2 times NO. But since NOBR2 is a intermediate, I'm going to go back and say, well, where did that come from? And I notice in this first step, this is a fast equilibrium step, that my NOBR2 is being formed from one NO and one BR2. So I'm going to substitute that in. So instead of, and here's an example of how I'm substituting that in. So overall, my rate law is going to be NO times BR2 times NO. So it's NO squared times BR2 is my rate law for the overall reaction. So you cannot have an intermediate involved in the rate law. Keep that in mind.